function with cover?
I think it's also to protect.
Yeah, to protect the concrete, the reinforcements, to protect this from the corrosion, the atmospheric corrosion, tolerate other environmental factor, and also this one aspect to protect the reinforcement. Another function is to ensure good bonding force between concrete and steel reinforcement. Because if the color thickness is too thin, the bonding force will be very weak. It's easy to crack. So actually, mainly because this two aspect reason. One is to protect the reinforcement, another is to ensure the good bond between the steel and the concrete. It's an important index for the durability design. So this concrete cover. Now the third part, we see some of the arrangement of the steel reinforcement. First part, we see the steel reinforcement in the slab. See this one, this T-beam, and the deck. On the top is the deck of this beam, deck of this bridge. Actually, this deck is on top of the plate, the slab. But according to the supporting condition, this slab or this plate, we can divide it into a different situation. For this outside part, actually is a cantilever plate, because just one end is fixed on the beam, and another side is just cantilever. And in the middle, this plate, this part, see, at this end is supported on the this beam is a transverse beam, or how to say this word? Check. I forget his name. The diaphragm. Is this one? Diaphragm. No. Go back. See. Transverse setup. Diaphragm. Use this word. Instead of diaphragm's distance, diaphragm. So, you know this word? Diaphragm. So, because between this two beams, see, for this picture, this one is the T-beam rib. This one is the T-beam rib. And normally, this T2 if we use T-shaped beam, this one is a separated one, this is a separated one. How to make it working together? So we need to in this transverse diaphragm to connect this together. So you see this in this middle, this part, and this end is supported on this diaphragm transverse beam. Actually, it's transverse beam. And in this direction, actually you can look at it supported by this rib. So that means both sides is supported by something. It doesn't like this side or this side. It's just a cantilever. So it's two different supporting conditions. So based on the mechanical feature, the slab is classified as the first type is a cantilever slab, and the second is a slab with a four-side support. If the short side direction be allowed, it's called one-way slab, otherwise called two-way slab. So what's the meaning of this one-way slab and two-way slab? It said if the short side direction bearing load. If I have a plate, suppose that's the place, here's the rim, here's the rim. Or we see this, well, this is the middle part supporting this four side all got support. If you put some load only on this plate, on this slab, which way do you think the load will transfer to the support? Go this way or go this way? So suppose this part is a very heavy mass or very large force. If you see, you put a very large force at this point. Also, at this four side, we all got support. So do you think in this way or this way the force will transfer to the support?
If the beam is like this, exactly?
No, we can ask one friend. So this one the plate. This end we got the support. This end we got the support. And this side also got the support. Just like this, just like the middle part here. So if there's one of the car or there's one of the car on the deck, on this part there's one car. So in which way do you think the weight of the car? In the final, the weight, the force, the self weight of the car, you have to transfer to the ground. So at this both four side we also got support. How do you think the weight of the car transfer to the support? So this way, or this way, have the force. How the force
distribution? The force distribution?
Yeah, the force distribution. How is this force distribution?
I think it's all the direction.
All direction.
Yeah.
Yeah, in the real situation, it should be every direction to have. But which direction do you think is the main will transfer the main part of the force? Because it cannot be every direction the same.
Okay, the side, those who are near.
In this short distance.
Right.
Yeah, that's right. But why?
Because I think because of the distance.
Distance.
Yeah.
Yes. Actually, distance just like have you ever learned the electron what's it?
Electron circular. The electron circular.
电 electron or electricity, yeah, electricity. Because if you got this battery, you got the wire. If you got here, got a lamp, you can go to the right. But if here you got another line, there's no. It should be what's the 电阻 是
lights. Our lights.
电阻 resistance, yeah. When there's no resistance, we say it's a short
Short circuit.
yeah, loop.
Cold circuits.
Is this one? Short circuit. Yeah, short circuit. If you make another short circuit, of course, electricity will go this way. They will not go this long way, and this solution is not because of the distance. Even this is the short way, the short circuit. The electricity will go this way because it got the resistance. Just like this. The force, if you go this way, you need to spend more time, and because if the force transfer through the plate, the force needs to make the plate deformation, then it can go through. This way, it will spend less effort and short time can reach the short and the support. So for this solution, maybe part of the force will transfer in this direction, the short side direction. For this plate, this dimension is A, this dimension is B. So A direction, if A divided by B or B divided by A larger than 2 or A divided by B is smaller than 0.5, we call it one-side slab. So the force, we consider the force is transferred along this one way, the short dimension way, we call it a one-way slab. If the dimension with A and B divided by A is smaller than 2, that means with the next line to here, something like this, nearly to the square, not rectangular, maybe square, like a square. Then, at this region, the force, as you said, will go every way. Yeah, nearly to this both direction, but we'll have separate this force, maybe just nearly the same. So, at this region, we call it two-way slab. So why we introduce this one-way slab, two-way slab? Because when you design the slab, when you design how much reinforcement you should put inside, you should know how the force will distribution in the slab. You have to put the correct position of the steel bar to resist the force. If for this two-way slab, if you only put the steel bar in this direction, that's not enough, because in this direction you also have a very large force. Because in this two-way slab, you need to boost direction, you have to put the mean steel bar. But if it only is a one-way slab, then the mean steel bar will be just in this direction. And in this direction, you just put the not important steel bar, just maybe distribution steel bar to fix this mesh of the reinforcement. And then you don't even need to calculation how much, just put it according to the requirement. But if two-way slab, both this direction and this direction, you need to calculation how much you should put inside. So that's why we divided this in two-way slab, because you have to know the real distribution of the force inside the slab. Unless you know the distribution of the force, you know how to calculation. So that's the one-way slab and two-way slab. The mean index is the L2 divided by L1, the long side divided by the short side, if it's larger than 2. If it is larger than 2, we see the one-way slab. If it is smaller than 2, we call it the two-way slab. In China we see the two-way 的双向板，单向板。但是的 one way slab 是 two way slab。one way 单向方向一个方向单个方向 one way two way slab 双向。So we see in this slab what type of force what type of reinforcement we need. The first type is the mean reinforcement. The mean reinforcement, the longitudinal tensile steel reinforcement. So in the one-way slab, steel reinforcement is placed in tensile zone. Also, the slab span direction, or the short side direction. The amount of the steel reinforcement is determined by the calculation, and they need to meet the requirement, construction requirement. The diameter of the mean reinforcement should not be less than 10 mm or 8 mm for this. One is for lane slab, another one is pavement slab. And the mean reinforcement located at the beam rib is bending according to this angle, 20 degrees to 55 degrees along the central X line of the slab. What's this mean? It's bending according to the angle. Next is, we got a figure actually, just a little. Earlier for the mean rib passing the support without bending, the number of the mean reinforcement is not less than 3 per unit meter slab, and it should not be less than 1/4 of the cross section of the mean reinforcement. And then the location of the middle span simply supported the slab and the support of the continuous slab. The space of the mean rib inside is not larger than 200 millimeters. So this is the requirement. The distance between this mean rib should not be larger than 20 centimeters, 200 millimeters. So the medium concrete cover C for the steel reinforcement, the lane slab should not less than the nominal diameter of the steel reinforcement and meet the requirement of the minimum thickness. So for this slab, the concrete cover should not less than if the reinforcement is 10 millimeter. Because you cannot be smaller than 10 millimeter, and also you should meet the requirement, construction requirement. Normally, 10 millimeters is too small. At least for slab, I think at least 20 millimeters. For beam, at least 30 millimeters. For distribution reinforcement, is a transverse reinforcement. Then it is said. So this is the second type of the reinforcement. Here you see this figure. On top of this support, you place the distribution reinforcement. this reinforcement is this. If this is a one-way slab, this direction, the short side which is the mean reinforcement, and this direction is the distribution reinforcement. Those reinforcements you don't need calculation. Just put inside according to the construction requirement. Maybe just according to this, the distance may be not larger than 200 millimeter, and the diameter not smaller than 6 millimeter. Something like that. Just put inside. You don't even need calculation. But for this mean shear reinforcement, you have to calculate the bending moment, the tensile force, something like this. That's this. The distribution reinforcement is a transverse reinforcement that is set at a certain distance for the connection to mean reinforcement, and is mounted by previous calculation. Actually, this you don't need calculation. The role of distribution reinforcement is to improve mechanism of the mean reinforcement and fix the mean reinforcement, resist the stress induced by the temperature and the shrinkage. So the main function actually is to fix the mean reinforcement. This is the mean reinforcement. This is the distribution reinforcement. The main function of this distribution reinforcement is just used to fix the mean reinforcement and also to resist the stress induced by the shrinkage and the temperature. Just like this. If you cut it this way, you see on the bottom is the mean reinforcement, on the top is the distribution reinforcement. This figure is cut it this way. You can see. So the distance should be smaller than 200 millimeters. And according to this code, CHBC, the bar diameter of the distribution reinforcement in the length slab is not less than 8 millimeter. The spacing should not be more than 200 millimeter. That's the basic requirement. And the cross-section area should not be less than 0.1% of the cross-section area. At the location of the bending on the steel bar, the distribution reinforcement should be set, and the bar diameter of the distribution reinforcement inside the work should be not less than 6 millimeter, and the distance should not be exceed 200, something like this. So this is sidewalk for the pedestrian is not so the load is not so heavy, but in the lane for the car. In the bridge in the normal lane for the car, the diameter should be a little bit larger, at least not smaller than 8. Here, the distance is the same, not larger than 200. For the sidewalk, it's a little bit smaller. It's not smaller than 6. For all sides for the two-way slab, two directions of concrete slab, both bearing bending moment, so it should be set the mean reinforcement along both directions. So for the two-way slab, this direction is not a distribution reinforcement, it's all mean reinforcement, and also need to calculation. So both this way and this way, that's for the two-way slab. If there's a one-way slab, over this way direction. So according to the real situation of your slab, so the reinforcement distribution is different. And for the fabricated slab, what used in the assembly slab, laying deck of the bridge slab is composed of several pieces of the precast deck using matching seam filled with concrete to be connected together. From structural analysis of the mechanical performance and the load, it's not the integrated slab, but a series of narrow slab beam that one direction bear load, concrete between matching seam of the various slab, known as the concrete hinge, bearing the shear force, so it's called the prefabricated beam slab. Therefore, the slab reinforcement layout of the precast slab is similar to that of the rectangular beam. Actually, here what's they talk about? Mainly talk about the concrete hinge. I find some picture maybe. See which one is good. I think your book maybe will have some of these. Also this. Maybe you can see this. This drawing is not regular. If you got to recast the slab, normally in the real situation, how we connect these two slabs together, working together? Actually, in this middle, normally they use like something like this. Inside they pour concrete, or the hinge is like it's like this. So that means if these two pieces of slab and the surface they connect together is not just a vertical smooth surface. They need to make this different shape to make this concrete hinge. This hinge can transfer the shear force. So just now, this length, what's the mean this length? For this prefabricated slab, also it looks like very large, very wide slab, but actually it works in the situation which is just like a different very thin slab, just working together. But in the real situation, when you design, actually you still can design as this thin slab, it's one-way slab design. You don't need to design according to the two-way slab, because actually in the middle they use the concrete hinge. Concrete hinge to just connect together. And this part we just talk is the reinforcement above the slab. It's sometimes compared to the beam is relatively simple, because in the slab only just the mean slab reinforcement distribution reinforcement. But you see This the normal skeleton of the beam reinforcement. See, it looks a little bit complete. At least compared to the slabs, it's more completed. So in this side, this circle, this rectangle one is stirrups, and on the bottom, this is the knee reinforcement. Actually, it's along the direction of the span. Is the knee reinforcement to resist the bending force. See, at some position, this knee reinforcement can bend up because we know for this simply supported the beam, the force, the moment is like this. The shear force is something like this. So in the middle span, the moment is very large, maximum. And when the position is going towards the supporting point, the moment is getting gradually smaller. So if you design this position, this section, maybe you need suppose 20 of the steel bar. But when you got this quarter position, maybe you only need maybe 15. And when you got this position, when you have 8 position, maybe you only need 10. Then, because when you design this position, you have designed 20. Then, at this position, you only need 10. So how about this another 10? If you still put at the bottom position, actually it's waste, it's no use, actually no much use. But for this figure, you can see, for the shear force, in the middle span, the shear force is the medium, the smallest. When the position is going to this supporting point, the shear force is getting larger and larger. So we can just start to like this. We bend this some part of this knee reinforcement bend up in this 55 direction. In this direction, this part of this bending up reinforcement can resist the shear force very effectively.
Okay.
And so beside this knee reinforcement and the stirrup, you see at this top corner, we also go to the horizontal reinforcement. So this reinforcement actually is mainly used to fix this skeleton. But because you can just imagine, if this two corner you don't put the steel inside, the stirrup cannot just stand there, just fall down. So this two corner, the steel reinforcement actually is just used to fix this stable skeleton. And also beside this part, beside this reinforcement, see this figure, sometimes we still need to add some of this oblique steel. So beside the bending steel, we still add more oblique steel inside to resist the shear force. Sometimes only the concrete and the bending up steel is not enough to resist the shear force. You need to add more oblique steel to resist the shear force. So at the top is the erect steel. It's called erect steel. It just make this skeleton stable. And also sometimes we also got this horizontal at the outside of the stirrup. We got the horizontal steel bar. Actually, the steel bar is used to resist the shear force induced by the temperature shrinkage, something like this. I find some of the real picture for. 钢筋。 always for column. One for column. This is something like this. At this side, those horizontal steel bar actually is used just to make this skeleton more stable and resist the stress induced by temperature and shrinkage, something like this. Those steel bar sometimes you don't need to calculation, just put inside according to the construction requirement. And the main thing you need to calculation is like this. Those mean steel bar on the bottom, and also those is the stirrup. Of course, study to fix to make a circle, because on the top is still got the plate you haven't finished.
Coffee.
Nothing else.
Yeah, we should like in all the space we have put concrete. In the whole space they will put concrete.
No. This is the box girder. Actually, after they finish this is the steel, they have got an internal model. The thickness of the plate. Actually, the fundamental shape is something like this. So now you see the steel bar is in this area. Once they put this model, this model inside.
Yeah.
And then they will.
Here is empty. See, from this figure, I think you can see. So this is the books. Here is empty, is the books inside. Yeah, actually it's like this. Yeah, this one is the. Yeah, this one, see, in the internal model is also installed.
Is it a bridge or?
Yeah, this book's good. Yeah, this for one bridge. You see, those pipe is for the pre-stressed.
Test shape.
Yeah. So this is the skeleton reinforcement for this beam. For this skeleton, we have two methods to form this skeleton. One is the weld method, one is the bending method. Bending method is just use the very thin steel wire to just bend it together. Weld is just like this. This is the weld skeleton. This type is just binding together. So two different methods to make this skeleton. So category of the steel reinforcement. They are longitudinal steel, tensile steel reinforcement, bend and inclined steel reinforcement, secondary reinforcement, and longitudinal steel rebar. Actually, it's distribution reinforcement actually. The mean reinforcement, longitudinal reinforcement, is divided into the mean tensile and compression steel reinforcement, have concrete in tension and compression to improve the flexural loading capacity. The mean longitudinal reinforcement is determined by calculation of loading capacity and meet construction requirement. The bar diameter is normally in range of this 12 to 23, and normally smaller than 40 millimeters. The arranging rule for the mean steel reinforcement of the beam are arranged in a layer as possible to reduce the layer of the mean replacement. So to increase arm and so save steel bar. So that's what's the mean. For this, to arrange in a layer as possible. So if you can put in one layer, one row, and it's better because you put the outside, the central side, the central of this position to the neutrals the arm. The arm will be large. If you put in 2 or more layers, the central side, the central is going up. Going up means the arm becomes shorter. So become shorter, you see the force multiply this arm, you see arm equal to this moment. That means you need to more steel bar. Once arm becomes shorter, that means you need to force the steel bar become more. So if you can put in one layer, then you can. That means you can increase the arm. That means you can use small reinforcement to reach the same, to resist the same movement. So for bending skeleton, the layer of the mean bar is not more than 3 layers. So that means if the skeleton is made by bending, you can normally the steel bar is not more than 3 layers. Cover at the bottom is larger than the diameter. When arranging 2 or more layers, general principle, the arrangement, the upper and lower steel should be aligned and symmetrical layout. That means the distribution you should make is aligned and symmetrical. You cannot make in this side you got a 5 or in this part you got a 2. You should make it in this line is symmetry according to the middle. Is symmetry. And the medium concrete cover steel reinforcement should not be less than the nominal diameter of steel and should meet the specification. For example, with a bridge located one half of the environmental condition, the mean steel bar in the reinforcement concrete and the bottom concrete, and the mean bar nearest the beam side and its concrete cover should be not less than normal diameter and 30 millimeter. So cannot be smaller than 30 millimeters. And if the steel bar is supposed 22 or 23, then your cover thickness cannot be smaller than this diameter of the steel bar. If the concrete cover in tensile reinforcement is greater than 50 millimeters, steel reinforcement grade should be placed with a bar diameter of no less than 6 and space of more than 100 meters. This means you need to add another grade for the to strengthen this part. If the cover thickness is larger than 15 millimeters. That means the concrete is very thick. You need to add some granular reinforcement inside to strengthen the tensile. For the space of the steel reinforcement is slating, when the layer of the reinforcement is 3 or below 3, the clear transverse distance of the main bar and the space between the vertical layer should not less than 30 mm and not less than the bar diameter. When the layer of reinforcement are above 3, it's not less than 40 and not less than 1.5 times bar diameter. So if it is a 3 layer, so 1 layer, this 2 layer, this 3 layer, the distance should not smaller than 30 millimeters. See this figure? Yeah. The distance actually is a net clear distance from surface to surface, not from the center to center. So here, the clearance of this 2 layer is larger than 30 millimeter. The surface to surface, the clearance it cannot be smaller than 30 millimeters. This is for the banding slating. For this type is for welding slating. Welding slating, all this layer is just one layer by one layer is welding together. And for this, you see, they have different requirements actually. This is the cover thickness, and also you got this cover thickness for the syrup, 20 millimeters, something like this. This at the corner because of the erect steel, and this for this welded steel reinforcement skating. There's no gap between this vertical multi-layer, no gap, just one by one. And the number of the layers is generally not more than 6 layers, And spacing requirement is just like here. See, if this two line, two column, this the distance, the space between this column should be larger than 40 and larger than 1.525 for the diameter. And for the distribution, for this longitudinal reinforcement, actually, they use the level the distance 15 millimeters like this, and also this the cover thickness at least larger than 20 millimeters. The syrup is defined by loading capacity of the incline section and meeting construction requirement and must be set within the beam. So in the beam, this syrup you have to put inside. It cannot miss it. Root syrup is to enhance the shear capacity of the beam and form skeleton with the longitudinal reinforcement, and to fix the location of the beam bar. The bar diameter of the syrup is larger than 8 mm and is greater than quarter of this bar diameter of the mean steel reinforcement. Spacing can be found in the specification. And also for the form of the syrup includes the closed one, 4 lambs, 2 lambs, and 1 lamb, different type of the syrup. For the lamb number, single lamb is generally not used. Double lamb used, generally single hoop, double slab, and different type of this. We can normally in those figure actually see it's not very clear. Here. Those circle is syrup actually on this beam. it's just one two lane. See for this, actually this is a stereo. This side is also called stereo. Those stereo. See on top of this circle is stereo. This is the in the box actually normally we don't do like this because the top plate normally you finish the two sides of the bottom and then you place the top reinforcement and then put the concrete. Just like this, the total steel reinforcement or the face, this region is very rare. It's a little bit difficult. That means that you have to put the inside model, put the inside and put concrete on put all this. It's a very large amount of the concrete.
Very large.
You see that this box is actually very large. Maybe it's 2 meters high, more than 2 meters high.
C'est pour faire le tour.
Ah non. Yeah, maybe this. Let's see. No, it's a box girder, not box girder. So this right is the stereo actually for this rib.
Allow shape. Inside, what we put inside, like after to put the bin inside in that space, what do we put?
This plate?
Yeah, inside.
It's also plate. Find some picture you see. It's like something like this.
Ready-made plate.
Inside and the cooperation with the outside plate fix this box girder.
And
maybe it's not very clear. See like this. This is the outside plate model, and this one is the inside model. Just like this. You see to put it inside. So this one, this is outer model, this is the inside model. And in this middle you put the steel, spaghetti, concrete. Press the tube.
And after we will not remove it.
Yeah, you use it actually inside. They got some supporting things. After you finish it, they just contract and this. Yeah, something like this. Contract and they remove it and then they pull out. This is inside they got some supporting. This supporting can remove and they just throw it outside. You see this got this supporting. You can just pull inside. Something like this. Maybe we'll have a rest. 50 minutes.
Rest.
steel reinforcement. The construction steel reinforcement. See, belong to construction steel reinforcement. That means those elements it does need to calculation. Just put inside according to the construction requirement. Just the diameter is larger than the minimum diameter. The distance cannot be smaller than minimum distance. Then it's okay. The need to calculation. Its layout is designed according to the construction requirement. Its rule is to resist the stress induced by thermal and concrete shrinkage and prevent concrete crack induced by shrinkage and temperature. And the bar diameter varies from 6 to 8. And when the beam is high, the longitudinal steel reinforcement is arranged along the both sides of the beam rib and the lateral side of the stirrup. Area is 0.001 pH. Spacing and tension in the web should not be greater than the watt beam and should not be greater than 100 millimeters. And the temperature should not be exceeded 300 millimeters. So the second part is really about the steel reinforcement in the slab and the beam. Because in this slab and the beam, there's a lot of different reinforcements. Besides the mean reinforcement, we also go to the stirrup, the erection, and the distribution reinforcement, something like this. And we see the third part. Third part is about the failure mode and the mechanical behavior, the whole process for the flexible member. The failure. So in this part, we introduce the one of the experiment, and based on the result of the experiment, we introduce the working phase versus the working phase of the reinforced concrete beam, and sum up the failure mode of this flexible member. So the experimental research. Because we know that the reinforced concrete is made of the sand, water, snow, something like this. It's not a uniform or homogeneous material. It's a composite material with different physical and mechanical properties. So it's a non-homogeneous, non-elastic material. So it is not consistent with the Hooke law after loading reaches to some extent. So you know the Hooke law. What's the Hooke law? Hooke law. What's the meaning of Hooke law?
It deals with this thing.
The law.
This thing. Or is it the extension, like the string? It deals with it.
Yeah. The deformation and the force is in a proportional relation. It's just working like an elastic material. So this is the Hooke law. But for the reinforced concrete, because it's not an elastic material, so when the force reaches some extent, the result is not proportional. So theoretical and the experimental result is very different. So the calculation of the reinforced concrete must be established based on experimental investigation. So in order to address the mechanical behavior and information of the normal cross-sectional beam and the load, we designed one of the test. A simply supported reinforced concrete beam with a span of 1.8 meters, and the longitudinal bar diameter is 2, 5, 10. So this symbol means is a rib. It's not a round steel bar. It's a ribbed steel bar. The round steel bar is just use this for this symbol. Rib, normally something like this. Measured prism compressive strength of concrete beam is FC equal to 20.2 megapar. And the measured tensile strength of the longitudinal reinforcement is 395 megapar. So that's the given conditions. So this is the figure of this beam. You see, this is a rectangular beam, 2 fed 10 millimeter steel bar is in this position. He got one A, B, C, D, E 5 points to measure the strain. Use the strain gauge to measure the strain. And see the steel bar. See this is strain gauge. Just stick to here. And at this position, you see there's no stirrup. At this part and this part, we got the stirrup and the longitudinal force. And in the middle part, only got this longitudinal reinforcement, and there's no stirrup. We put stirrup inside to resist the shear force, but in this part we don't put the shear force. We don't put the stirrup inside. So we just to see what's happening under the force. See, we put two concentrated forces at C and B, and the supporting body is A, B. So for this type of load, this support point and these two concentrated force, the bending moment is like this. Because it is a concentrated force, the figure is a straight line. If this is a uniform load, the figure is a curve. I think you have just learned structural mechanics. And this is the shear force. You see, the most important thing is here. In the middle part, there's no shear force. Because we use two concentrated load, and these two values is equal, is the same. So in the middle part, there's only bend moment, there's no shear force. So the test beam is a rectangular beam and simply reinforced, singly reinforced. So what means singly reinforced? Singly reinforced, we have introduced, it's just that we put the mean steel bar at the bottom, at the low part. Sometimes we also put the steel bar at this top part. That means doubly reinforced, not single. Now we call it singly reinforced. Using hydraulic jack to impose two concentrated load F, and the diagram of the bending moment and the shear force as we just will see. The shear is 0 in the CD section, and this section is shear is 0. There's no shear force. But the bending moment is a constant. Yeah. In this part, the moment is a constant. Constant is fixed value. So this part is known as full bending part, which is the main target of experiment research. So to understand the failure process of the reinforced concrete beam, deformation feature, and the mechanical behavior of cross section and the limit load is tested to develop strength calculation formula for this RC beam. For this is the result of the test. We see from this figure, we can see can be divided to 3 sections. One section to here, you see, the deformation and the force is actually nearly in proportional relation. And then this part, the beam is working with no crack. But at the end of this part, if we get into this second part, the crack will generally appear. And with the load increase, the crack will increase greatly. At this position, you should know once the crack appears, the tensile force we just use the assumption the concrete no longer resists the tensile force. All the tensile force was transferred to the steel bar. That means at this position, they have got a redistribution of the stress, tensile stress. So we see this figure, this distribution. Then there's two characteristic points, and the mechanical and the deformation was divided into three phases. First one is the overall working phase without crack, and the first two is working with crack. The phase 3 is the failure phase. Crack propagate sharply, and still stress maintain the level of the yield stress. So that means that at this position, at this second, the part, the steel reach the yield stress. We know when the steel yield is when the steel reinforcement reaches its yield stress, they can have a very large deformation. The strain will increase greatly. After some extent, it can go to strengthen. So that means at this situation, at this stage, the crack will develop quickly. Even the load doesn't increase, the crack will increase equally because deformation of the steel will develop very quick. So at this stage, the crack. So what will happen with the increase of the crack? You can imagine. This steel, this is the neutral X. Here is the compressed. Once the crack here, then crack is here, and with the load increase, the crack will increase. The crack develops quickly and become longer and large. Do you think what will happen to this neutral X? The position of the neutral X will move down, move up, or fixed. This neutral X will this neutral X position will move.
So we'll
no, this X, this neutral is this one? Neutral X, just like the central of the section. But if the lower part have a large crack, that means the effective section will be just like remains like those parts. So that means the central X or the effective section will go up here to here. So actually, the actual will go up to here, gradually increase, move this way. Because here this part is already cracked. Cracked doesn't mean that concrete actually doesn't work, quick work, no use actually. So with the neutral X going up, that means the area to resist the compress becomes smaller. The area becomes smaller, that means the compressive force increases greatly. And with the development of the crack, the compressive force of the concrete will increase greatly, and they quickly will reach the compressive strength. Once increase the compressive strength, the concrete will be crushed. That means first the steel reaches the yield strength, and following this, the concrete on the compression tool will reach the compressive strength and be crushed. Then the beam will destroy. You see this and this second phase, the crack appear, and the third phase, the crack development and the concrete was just crack through. So three characteristic points. For example, the end of the phase 1 presented by RE here. Crack will appear soon. The end of phase 2, longitudinal still approximate yield, and the end of the phase 3, concrete in comparison was crushed, and the entire cross section of the beam is damaged. So this figure, yes, figure 315 shows the section average strain of the concrete and the wedge load and corresponding stress distribution. We'll see in this figure, with the increase of the loading, the strain of the concrete is also increasing, but the strain diagram is basically a symmetric triangle. Also found that the neutral axis gradually increase with the load increase. So this figure we can see. At the beginning, this is the phase 1. And the first part of the phase 1 is all in straight line triangle distribution. That means the strain and the load actually is in proportional relation. And then generally at the end of the phase 1, you can see in the tensor this line actually is not straight line. It generally have become some curve, because at this position the concrete is going to generate a crack. So it's nearly reach the tensile strength of the concrete. So it's no longer elastic. It's no longer proportional relation. Generally become this curve. And at the phase 2, the crack appear. Once crack appear, say, based on our assumption, we consider the concrete quit work. They don't bear tensile force. All the tensile force was transferred to this steel bar. So only the compression zone bear the compressive force. All the tensile force is resisted by the steel. And then with the loading just keep on increase. See, in the compression zone, the compression force, the distribution is also become curve. It's no longer straight here. So that means that
crack increase.
Yeah. Also, you see, compared with the phase 1, phase 2, you see the neutral axis at the phase 1, neutral axis is in this position. At the phase 2, neutral axis actually is going up a little bit. And then reach phase 3, compared with phase 2, the neutral axis keep on going up. And also the distribution of the compressor is more, and finally, at the end, the steel reaches yield force and the concrete reaches compression strength. At this part, compared with here, you see, the biggest compression force is not at the top, it's in this part. Why this happened? Because the stress strain curve of the concrete, if you remember, is something like this. Once the stress is to some extent larger, the stress is no longer the largest stress is not compared with the last strain, because at this top, of course, at the top of this position, the strain is the largest, but then that means the stress is largest. The largest stress may be at this position. Maybe this here is 0, 0, 0, 1, 9, and 0, 0, 0, 0, 2, something like that. So at the end, the largest force, that's stress, compression stress, is not at the top. Actually, it's a little bit lower. So sectional stress must be calculated from the stress-strain relation and show the curve. Just we see it here. Those stress is calculation from the strain, because from the test we only this point we use the strain gauge. The result we measured is strain. How to get the stress? We know the strain, how to get the stress. We just use this relation. It's not just stress equal to strain, not this symbol. Only this state is correct. Once going up to this, it becomes curve. This is no longer useful because it's not elastic, it's not proportional. So we need to use this figure to calculate stress. If we only use this, what result we had? The biggest stress always hit this point. Because the strain is always at this point, the strain is the largest. So this figure is the tensile test for the steel method. This is the actual compression with concrete. See this curve. This is the tensile of the concrete. Actually, we normally use this part is in this formula. The real situation is like this. So this stress and deformation of the beam is divided into 3 stages, namely this phase 1, 2, 3. For phase 1, the full processing of the concrete works, and the concrete compression stress and tensile stress basically follow triangle distribution. Longitudinal steel carries tensile stress. Concrete in the elastic state. Nothing to say. Concrete stress is proportional to strain. At the end of the phase 1, the stress of the concrete in comparison to is still in triangle distribution. However, the plastic deformation of the concrete in tensile to rapidly. As the tensile strain grew quickly, according to the stress-strain curve, the stress diagram of the concrete in tensile to appear a curve shape. Meanwhile, tensile strain of the concrete in tensile 2 is near ultimate tensile strain. That means the crack is going to appear. Once it's reaching the tensile strain of the concrete, just crack. So actually, the tensile stress reaches the tensile stress of the concrete. That means the concrete will crack. That means crack will appear and the bending moment increase imposed on the beam is bending moment imposed on the beam is what's this? This crack, that means critical near the concrete. And for phase 2, bending moment and the load reach this. And the weakest section of the tensile strength of the concrete on the beam is show crack. At this time, there's crack in the cross section, and the concrete in crack section quit work. This results in tensile bearing bed by concrete transfer to the steel reinforcement, and so there is the significant stress redistribution. And the tensile stress of the steel reinforcement increase with the increase of the load. Concrete compression stress appear no longer triangle and form the slightly bent curve shape. And the neutral X move upward. Just now we have introduced. At the end of the phase 2, tensile strain of the steel reinforcement reached the value that the steel bar yield, which indicates that the steel ring stress reaches yield strength. And for the phase 3, tensile strain steel reinforcement increase rapidly, but the tensile stress generally remain a level of yield stress. So the strength increase greatly, but the stress just remains nearly the same level. Then the crack propagate quickly, and the neutral X going up continuously. Concrete compression zone reduced, and the concrete compression stress increase. The compression strain diagram appear in a full curve shape. End of the phase 3, the concrete compressive strain in top zone reach its ultimate compression strain, and the compressive stress block show curve shape. While the maximum compressive stress is not located at the top edge, but on the edge of the concrete section of the compressive strain block, but a little down from the top edge. Then this is determined by the stress strain diagram. So end of the phase 3, the compression stress of the concrete in the compression zone exhausted, and the horizontal crack appear at the both sides in a certain section. Then concrete crashed and the beam fell. At this stage, the tensile stress also reaches yield strength. So from this experimental research, the mechanical characteristic of the single reinforced concrete beam can be populated like this. So compared with the homogeneous elastic beam, homogeneous elastic beam actually is the target of the material mechanics we have studied before. M is proportional to the sigma, and the location of the neutral X. The shape of the stress and the strain diagram keep unchangeable, and the only quantitative change happen. It's very simple, just an elastic material. But for this reinforced concrete beam, the value of the sigma changes as the M increase. At the location of the neutral X, the trace diameter change, and the beam working with crack at most of the stage, M is not proportional to this sigma. That's the most of the difference. And the ultimate compression is normally we use this 0.003 in CHBC. The neutral X increase with the increase of the loading, and which is resulted by the static equilibrium and the stress change and the cracking condition. For this phase 2, the neutral X change a little, and the arm of the internal force keep basically unchanged. Increased stress is used to resist the external bending moment. And for phase 3, section stress is unchangeable. In order to maintain the second cross-section static balance, the arm of the internal force increase and the neutral X move up. So that means at this compared with phase 2 and phase 1, the neutral X just move up a little. The main change is in the stress of the steel bar. The steel bar, the stress of the steel bar increased greatly. And compared to phase 3 and phase 2, the neutral X actually increased a little more. And the stress in the stress of steel keeps nearly unchanged. Because once if you want to keep the section balance, you have to, one side is increase the stress, one side is increase the arm. So now, the stress of the steel bar already reaches the yield stress, cannot increase anymore. Then you have to increase the arm. That means the new tracks have two going up. Once the new tracks going up, the compression zone just reduced. Compression zone reduced. That means the compression stress increased for the concrete. So nearly just with the loading increase, that means will soon just will crash.
So, Laushi, how can we move the neutral? How can we do that? How can we increase the hand? The hand. How can we do that?
How can we?
Yeah, if there is a crack, the neutral is there. How can we move it? How can we
It's
put it
move automatically.
So we don't have the if when there is a crack, when we observe that there is a crack and it's not brittle, a crack in the structure, how can we prevent it? How can we make sure that the bridge will not collapse?
That means you need to make sure the concrete will not crack. You use press stress or something like this.
But if it's happened that we observe some crack, how will we do it?
Actually, lots of the reinforced concrete beam working with the crack. Small crack is no problem.
Oh, okay. Okay. This is what I wanted to know.
Yeah, but if we working with the crack, that means the durability will reduce. It's easy to be infected by the atmosphere or something like this. But for the loading capacity, if your reinforcement input have correct the reinforcement ratio, I think it doesn't matter. Just the reducibility may be, durability may be just maybe you designed 100 years, maybe 80 years, something like this. It's not good.
So Laushi, when we have designed a bridge for 100 years and then the 100 years finish, how we do? We should how can
we still can use or make to strengthen it. We
have to strengthen it.
Maybe I will not reach 100 years almost destroyed. For design for this building, also at the present, most important structure, the design period, design life is 100 years. After 100 years, maybe this building is still okay, you can still use, but the safety factor is reduced. You should be careful. Maybe suddenly somebody
just a wink.
Yeah, so that's what happens. So yeah, because in this 100 years, we can have 95% guarantee for safety. Yeah. After 100 years, maybe you got 80% guarantee or something like this.
Like for example, if we say the example of the Eiffel Tower in Paris. Is now how many years? So do we think that after 100 years it will still be good?
Yeah. Yeah. This is the question of the probability. 1% probability or 20% probability. Actually, at the normal time is the same. Once happens, that means just the chance. The structure failed or destroyed, the chance is large, but the probability is large. You cannot just compare that it's safety or not. It's very difficult. So just the safety factor is lower, something like this. Okay. Thank you. It's 10 o'clock. Have lunch.
Oh.